Okay. All right. If there are no more questions, again, feel free to ask. If you come up with some questions later on, you can also type them in the chat or after the lecture into the Teams channel. I want to go now on to today's lectures. Let's see how we're on time. My idea today was to go through slides related to greedy algorithms and also start with the basic concepts behind meta-heuristics. So if whatever we don't finish today, we'll continue then the next week. All right, so lecture 4A, and I hope everyone's, so I uploaded the slides this time a little bit ahead. So yeah, I uploaded them yesterday. You have them on Teams. You have them also on Fair Web. I'm sure you're all more or less familiar with this concept of greedy algorithms. What are the defining characteristics? First of all, we're looking at iterative and constructive heuristics. So what does that mean? First of all, we start with an empty solution. So when we say we're looking at a constructive algorithm, in each iteration, we're trying to fix a certain solution component, certain solution component. For example, we're looking at finding this shortest Hamiltonian cycle in the traveling salesman problem. We start at the first city, then we add the next city to our path, then the next city, and so on. Once we have added a certain component, it is fixed, and we don't change it later on. We just keep going. So in that sense, it's constructive. Once we have completed our tour, we have a final solution, and we're done. Okay, so in that case, in that sense, we've constructed a final solution, and we're done with our greedy algorithm. We also say that these decisions are myopic. And what that means is that the decision on how to proceed in each iteration is based on a somehow locally optimal decision. So we define some kind of a heuristic in each step that maximizes an immediate benefit. So we have some kind of a greedy function. For example, if I am at a certain city, solving the traveling salesman problem, I look at which city is the next nearest city, and I go there. So in that sense, I have this greedy step or greedy approach where I'm looking at the locally optimal decision. So these are some general concepts, and like I said, we'll go through today the general concepts behind greedy algorithms, and we'll look at some examples in terms of these various combinatorial problems that we have talked about also previously. So we'll get back to these. Looking at our classification that we talked about also previously, we said that when we can split between exact methods and approximate methods. Hold on, turn on the pointer again. Exact methods and approximate methods. We talked now last time about branch and bound dynamic programming as examples of exact methods. When we talk about approximate methods, we can look at approximation solutions, which approximation algorithms, where we have some kind of a guarantee on the bounds, how far we are from what are the bounds in terms of our distance from an optimal solution. But for heuristics, simple heuristic algorithms, we generally don't have let's say, a guarantee on how far we are from the optimal solution. We're going to look at constructive heuristics in terms of greedy algorithms. We'll look at some hybrid approaches. So next time when we talk about local search, then we'll combine local search and greedy algorithms and talk about GRASP, which is greedy randomized adaptive search. And then there are improvement heuristics or meta heuristics, where once we have a certain solution, so as opposed to constructive, where we start with an empty solution and construct an initial solution, with improvement heuristics, we assume we have either one solution or a population of solutions, depends on whether we're using a single or population-based heuristics, which we then try to improve. So going through each iteration, we try to improve that solution. Okay. Oops. All right. So greedy algorithms, like I said, we're talking about constructive heuristics. We start from an empty solution, construct a complete solution by assigning a value to a decision variable one at a time. So for example, again, if we're talking about the traveling salesman problem, it would be, we decide which city to add to the tour. If we're talking about a knapsack problem, we're deciding about which element to add to our knapsack or add to the knapsack and so on. So we assign a value that somehow maximizes this profit, and that's why it's called greedy. And what we'll see is that this can be either static or dynamic, and we'll get to that in a moment. When we look at, let's say, typical characteristics of greedy algorithms, generally there is no backtracking. Of course, I mean, what I'm talking about now are just some general, let's say, general characteristics. Of course, you can have modified algorithms and so on where you define whatever it is that you want. But in general, what we're talking about, no backtracking. So once a decision variable is assigned a value, it's not changed. So we keep going. Okay. What are some advantages? Well, first of all, the greedy algorithms are a good way to obtain somehow an initial solution. For example, if we do have a problem, it's a good way we can maybe define a very simple algorithm where we, like I said, take the next, pick the next element which has the highest value or the lowest price or is the nearest distance or so on. Easy to implement. And it gives us a starting point. So it's usually fast, less complex than some kind of improvement algorithms. If there is no stochastic component, then this is usually deterministic. So what that means is that if we define our greedy algorithm, if we start always at the same point, we will always end at the same solution if we have some kind of a deterministic greedy step. So if we're not using any stochastic component, then we will always end deterministically. Okay. What are some drawbacks? Like I said, we're looking at this local or so-called myopic view, which of course does not guarantee a good global solution. Just because something is locally optimal or seems to be at a certain point, an optimal solution does not, of course, imply global optimality. Another thing is that the solution quality is very dependent on the problem instance. So not just the type of problem, but specifically the structure of the instance which you're looking at, the actual graph or the elements or so on. So for certain instances, a particular algorithm may give you a very good solution or a starting solution, whereas for a different instance, it of course may be a much poorer solution. So that's why we can't really, it's hard to make a robust algorithm for all problem instances. Another thing is that if we stop the algorithm somewhere along the way, we are actually looking at an incomplete solution. So we have to run the algorithm all the way to the end in order to construct a complete solution. For example, a complete tour or assign all of our decision variables. Okay. So what are some basic design issues? First of all, this solution representation is a key thing. The solution representation, and we'll talk about that also in the next lecture, stating how we're going to define the elements which comprise the solution. So is this, say, for example, a binary vector? Is this a permutation vector? Is this a vector of real values or some kind of, so how are we going to actually represent our solution to the problem that we're solving? When we look at a partial solution, that means that only a part of these elements have been selected so far. The selection, so that's the first design issue, is how is our solution represented, which will depend on the actual problem. And the second thing is, what is this heuristic or selection method in each step? So based on what is, how am I going to decide on what will be the next best element in the current list of possible elements? That's going to depend, of course, my objective function or the what it is that I'm trying to maximize, minimize, or so on. This heuristic will have to calculate then the profit of each potential element and decide which element now is best to add to the solution. This heuristic can be, or the heuristic that can guide this greedy step can be either static or dynamic. Now, what do we mean by that? When we say static, it means that the profit is calculated once at the beginning and doesn't change. Let's look at, for example, if we look at the knapsack problem, we have n elements. Each element has a certain value and a certain weight, right? I decide to add element 3 to my knapsack. Okay, now I have to decide about the rest of the elements. Their weights and values are static. It doesn't matter that I already picked element 3. Their weights and values have not changed, right? So they remain static, or their profit how much they contribute to the objective function doesn't change as my algorithm proceeds. On the other hand, if I look at a dynamic example, and let me show, hold on. Word. If I look at, for example, a path, okay, if I have a path here, I have a path here. So node A, node B. Let's say the distance to get from A to B is 7, right? If I'm currently at node A, so I've added node A to my path, the profit or the cost of adding B at that point is going to be 7. However, let's say I have node C over here. Let's say that these distances are 3 and 1. Now, if I'm currently at node C, the cost of adding B is going to be 1, right? So now the cost of adding B has changed depending on where I am. And that's what I mean by dynamic profit. So the profit of the next element is going to depend on where I am currently or how I've constructed my solution so far. Okay, just wanted to clarify that. Let me go back to the slides. Okay. This is just a very basic generic greedy algorithm. So we begin with an empty solution set. We choose a solution element or assign a decision variable, which brings maximal profit. And that's what you need to decide. So you need to decide what we mean by maximal profit to the objective while keeping it feasible, right? And we keep going until all solution elements have been either added or decided upon. Let's look at some examples. So again, the knapsack problem, given that we have 4 objects, let's say we have 4 objects and a knapsack of size n units. Each object has a value vi and a size ci. We're trying to decide on which objects to fit. So maintaining the capacity, so we're not allowed to go over 9 units, but we want to maximize the total value. If we take a simple greedy approach where in each step we simply take the most valuable objects, that would be then our greedy step. We take the value vi of an object which contributes most to the objective function. So in this case, we would first pick object 1 because its value is 8. So now we've already filled the capacity, right? So we're already at 9. A better solution would be by choosing, we could choose if we chose different objects, V2, V3, V4, we could get a total value of 11 and still maintain this capacity. One option, for example, when looking at the knapsack or the knapsack problem would be that instead of just taking the weight as the looking at the adding the element which has the highest value, we could choose, for example, the object that minimizes the ratio cost over weight, right? So ci over vi. We look at which object has a minimum value of that ratio and then add that object to the knapsack first. So that would be ci over pen is always over vi. Sorry, I'm keep losing contact. Okay, so that would be an example with the knapsack problem. Let's look at an example. It's 3 o'clock now. Is it okay if I continue just for 5 more minutes and then we'll take a break?
Yeah, sure.
Yeah, okay.
Okay. All right. Let's look at an example where we have let's say a private telephone network. We have a bank that has several local offices. They want to connect their local offices with their central office via a private telephone network. How should they do this? So how should they set up these links to minimize their costs? Let's say that a telecom operator offers prices for connecting each pair of offices, so we can connect each pair of offices proportional to their mutual distance. One approach would be to connect directly to a central office. A cheaper approach would be to try to find a minimum spanning tree, right? So this is an example with a telephone network. This could also, another example could be that you have, let's say, some data centers and you need to have certain servers where you're replicating certain content. You want to find the best, let's say, links how to link these different servers in order to minimize certain costs. And this is something that, for example, companies such as Facebook, Google, and so on do. So a minimum spanning tree would be a solution to this. And we know that if you've heard of Kruskal's algorithm for solving the minimum spanning tree, so this is an algorithm which will give us an optimal solution. And it's an example of a greedy algorithm, which is why I want to just briefly go through this. So given a weighted graph, a minimum spanning tree is a tree which connects all nodes in the graph at a minimum cost. And we have this greedy algorithm which finds an optimal solution. So what do? We sort all the edges according to the weight from the smallest to the biggest. And we always add the edge with the smallest weight such that it doesn't form a loop until we have n-1 edges in the tree. And at that point, we have our minimum spanning tree. So just as in a quick example, we have 7 nodes. Our solution is going to be comprised of n-1 edges. If we sort the edges going from the shortest edge to or the least weight to the largest weight, we start adding them here. So E7, E3, E11, E4. Okay, we don't add E2. Why? Because it makes a cycle. So no cycles allowed. We skip it. We keep going and so on. Again, E9 will create a cycle. So we skip that over here. And once we have n-1 edges, we're done. Okay, so very simple greedy algorithm, and the greedy step is defined with this minimum. So we always take the node with, or the edge with the minimum distance. Okay, that was simple. Let's look at the traveling salesman problem again. So let's say we have n cities and their mutual distances. We're looking at, again, these shortest tour. One approach, and this has a lot of applications in various domains. One example is the nearest neighbor. So simply we choose a city at random, always choose the city that's closest that has not yet been visited. Once all cities are visited, return to the starting city. This will be very dependent on the starting city. Again, this is an example of a dynamic step, as I illustrated before. So the distance to the remaining nodes is updated based on the current node in each step. That's one example of a greedy algorithm. Another one would be to choose the shortest edge, avoiding those where cities are n nodes to more than 2 edges. Okay, let me just briefly show these 2 examples, and then we'll take a break. So the first example, nearest neighbor. Okay, we start at node C, then we go to A, D, and so on. Okay, we have this distance. If we were to start at a different node, we would get a different solution. So we get a better solution in that case. So this is an example, and we see that clearly the solution to our greedy algorithm is going to depend very much on the starting city. The second example is where we choose the shortest edge, avoiding those where cities are n's to more than 2 nodes. Why? Because for each node, we can have only 2 edges, since we're allowed to visit each city only once, sorry, not twice. Okay, and this is an example where we have a static, actually heuristic, since these edges don't change. So we sort these edges according to from the shortest to the longest distance, and their values don't change depending on what we've added already to the solution. So we add AD, we add AB. We don't add AC because in that case, node A would have more than 2 edges. And like we said, you can visit each city only once. So it can only have 2 edges, a degree of 2. CD, BC, once we have n edges, then we are done. Okay. All right. Let's then take a short break now. What time is it? 3:06. Is it okay if we start again at 3:15? I know we're a little bit, it's a short break, but we have a lot to cover today. So if that's okay with you guys, we'll start again in 10 minutes.
It's okay.
Okay, great. So we'll stop recording now and see you at 3:15.